All right, so I've had a request to do problem number 47 and to really talk through how to think about it. So in this problem, we have a set of two capacitors. We have a positive plate, a negative plate, and then another positive plate, resulting in two different fields and a path going from A to B. Now, on the previous page, we learned that the electric field here is 725 volts per meter. The electric field over here is minus 425 volts per meter. A is at minus 0.4 meters and B is at 0.2 meters, and all of this is on the x-axis. Also, what isn't really that clear in the way the problem is written, this center plate is at the origin. All right, so we want to look at the path from A to B and calculate the electric potential. And then we want to do the same thing looking at the path from B to A. And then if we were to, we're going to say there's a tiny hole there and it's going to be a negligibly thin plate. What would the change in kinetic energy be if we moved an electron from A to B? And then lastly, what is the minimum kinetic energy the electron must have at location A to fight against that repulsion and get to location B? All right, so let's step through this together. So I'm going to just draw a picture so that we've got something to refer back to. This is always something I recommend doing. I've even been known when I took exams to draw pictures on exams that already had pictures. So I'm just going to write this, keep this all in X, and make this a little bit easier. All right, so we want to do delta V from A to B, so VB minus VA. And to do this, we want to break this into two pieces, so we're going to add point C here in the middle. That way each piece is going to have the same electric field. So VC minus VA is equal to minus E1 delta X is equal to minus 725 volts per meter times 0.4 meters is equal to minus 290 volts. And then we want to do VB minus VC, once again, equal to minus E2 delta X is equal to minus, so that field's in that direction, so it's going the negative, minus 425 volts per meter times 0.2 meters is equal to 85. And so from here we have VB minus VA is equal to minus 290 volts plus 85 volts is equal to minus 205 volts. Now we're going to want to remember these values for later on in the problem. All right, so part B, we're just going in the opposite direction. So VA minus VB is equal to minus VB minus VA, which is equal to minus 205 volts. So this is 205 volts. Easy peasy. All right, so now we're getting into the meatier part of this problem. And we want to know if we moved an electron from A to B, what would the change in kinetic energy be? So if we talk through this conceptually, the electron is going to slow down as it reaches the middle plate because it's going to be fighting that repulsion from the negative charges, and then it's going to speed up as it goes barreling towards this positive plate over there. So the change in kinetic energy for this for an electron, so we have delta K is equal to question mark. Now in this case, everything is inside of our system, so the delta E is 0. That's why we choose our systems carefully. So then delta U plus delta K is equal to 0. Delta U is equal to Q delta V. So we have Q delta V plus delta K is equal to 0. So minus E delta V plus delta K is equal to 0. Delta K is equal to E delta V. We've lost our negative sign to bring it over. Is equal to 1.6 times 10 to the minus 19 coulombs times minus 205 volts is equal to minus 3.28 times 10 to the minus 17 joules. All right. So for part D, this is where we need to be a little bit clever. So part D is we want to know the amount of kinetic energy that would be required to get the electron from A to B. So what you need to recognize here is once it gets to position C, then you're going to have that electric force pulling it forward. So you need just enough kinetic energy to overcome that repulsive force. If K is equal to 0 at this plate here, then that force is going to take over and act on it and accelerate it forward. So you can say that your final kinetic energy in this case is 0, and we really only need to examine going from A to C instead of A to B. So now that we have kind of the thought process down, we're going to assume the plate thickness is negligible, and it just needs to, electron needs just enough, obviously more will be successful, K to go from A to C fighting repulsive force. So it is going to slow it down. If it slows it down to 0 at C, then we're fine. If it slows it down to 0 before C, then that repulsive force will send that electron back towards the other positive plate. Okay. So, and then it doesn't, after it goes to B, it doesn't matter. All right, so once again, our change in E is 0. Delta U plus delta K is equal to 0. We would have Q delta V plus delta K is equal to 0. Then minus E delta V plus delta K is equal to 0. Delta K is equal to 1.6 times 10 to the minus 19 coulombs. And this time we want to just use that delta V from, we want delta V equals VC minus VA, which is minus 290 volts. So this is equal to minus 4.64 times 10 to the minus 17 joules. So we would have 0 minus Ki is equal to minus 4.64 times 10 to the minus 17 joules. And so Ki is equal to, we would then multiply both sides by negative 4.64 times 10 to the minus 17 joules. And this is, if you're curious, 290 eV. So essentially what's happening in this situation is that your electron has Ki non-zero, and it slows down until K equals 0, and then it speeds up. So it slows down, to a stop, and then speeds up. All right, and there you have it.